Good evening, everyone. I'm Laura Mosca. I'm the EAGE local chapter Paris president, and our today's webinar is about Svalbard Archipelago. And the topic of today is why did an Arctic glacier suddenly speed up? So in today's talk, our speaker, Dr. William Harcourt, he's going to explain about the project that he did in Svalbard to study the active surge of the glacier in the area using the different innovative technologies such as drones, seismometers, terrestrial laser scanners, and palaeo-glacier analysis. So you will hear that shortly. So let me say a few words about EAGE. The European Association of Geoscience and Engineering is quite a mature association. It's more than 70 years old. It's a non-profit association. It's all of us are volunteers, so we promote the development and innovations in geoscience and engineering fields for those working and studying in this area. And we have actually some really exciting news. We have several really big conferences happening this year, and one of the biggest events is the EAGE annual conference that will be held in Oslo in Norway. And it is one of the largest multidisciplinary geoscience events in the world. And this year's topic, it's about technology and talent for sustainable energy future. So it's a really, really big event. So if you can, please attend. And another exciting event here in Paris in 5 days' time is the EAGE digital event, which will be about the data storage and how we can store the data in the most efficiently, and to make sure that we use the best available technologies to unlock the right investment decisions. So that's here in Paris in 5 days' time. If you are around, then please join. And another exciting event is the EAGE Near the Surface Geoscience 24, which will be held in Helsinki in autumn. The call for abstracts are still open until 25th of April. So if you're thinking that you might contribute, then please do so. What is very interesting about this conference that it will have the following topics included in it, which is the geophysical survey of cryosphere and Arctic, which we are actually going to discuss today, as well as the geophysics monitoring the effects of the climate change. And there will be an entire panel meeting dedicated to airborne drones and robotic technologies in this conference. And why to join EAGE if you haven't done so far? So first of all, to get access to different geoscience and engineering resources, to get discounts on the big conferences and on the big events, as well as have access to free webinars and learning resources as well. There is a mentee and mentor program as part of EAGE. And as you can see on the map, we are present in many places in the world, but more specifically today, we have a presence of EAGE Paris. So the event is organized by EAGE Paris, and it's in collaboration with EAGE in Aberdeen. So you can look in the map and see which location is closest to where you're located, and join the EAGE local chapter there. So here in Paris, we have a team of 8 board members. We are very, very diverse team. We have nationalities such as Venezuela, Italy, Algeria, and of course France as well. And we always are happy to have new volunteers. So we recently have 2 two people joining our team, which is who are Carlos and Said. So very warm welcome to both of them, and we are happy to have great people joining our team here in Paris. So just to follow us, that's our a link to our LinkedIn page, where we post about all our events that we do, and it's the easiest actually to keep updated on of what we do. Okay, I will let Peter present the EAGE Aberdeen slides.
Okay, thanks, Laura. So I'm Peter Robotham, the president of the local chapter in Aberdeen. I'm not putting photos of our committee members up because we're not as photogenic as the Paris team, but there's a group of about 10 of us who organise events around Aberdeen. We also encompass other Scottish areas such as Edinburgh as well. And there are our contact details on this slide. And if you could forward it onto the next slide. Thank you. We've got two upcoming events in the very near future. So in 2.5 weeks, we've got a talk on the Morecambe Net Zero project. So using a depleted gas field as a potential future CO2 storage site. So that's going to be organised jointly with the Geoscience Energy Society of Great Britain in Aberdeen. And we're just checking whether we're also going to be broadcasting that talk. So look out for our LinkedIn page to see details of that. And then in Aberdeen on the 1st and 2nd of May, SPE are organising the Seismic 2024 conference. It's an annual conference, and that's supported by EAGE. So if you're in the Aberdeen area at the start of May, do come along to that. And I'll hand back to you, Laura.
Yeah, thank you very much, Peter, for the updates on Aberdeen. It's great to have you today on our webinar. So today's agenda, I did a quick introduction to the EAGE and the local chapter Paris and Aberdeen. I'm going to shortly introduce you to our speaker today, Dr. William Harcourt from the University of Aberdeen. Please feel free to write your questions in the chat during his presentation, but remain muted, and we'll have the Q&A session just after, once he's finished his presentation. So our today's speaker, many thanks, William, for accepting our invitation, is Dr. William Harcourt. He is the Interdisciplinary Fellow at the University of Aberdeen. He joined the University of Aberdeen in 2022. He holds a PhD degree from University of St. Andrews, and he's actually currently developing a really innovative project, which is the digital twins of the Arctic cryosphere in Svalbard and Greenland. He is trying to understand the glacier physics and how glaciers are actually changing, and if actually the impact of them changing are the result of the faster climate change. And he has a wide range of research interests which are across multiple disciplines such as glaciology, artificial intelligence, data science, and remote sensing, and many, many more. So yeah, thanks a lot, William. I'm going to hand the presentation over to you.
Thank you very much, Laura, for the invitation to speak here today. I guess this is going to be a slightly different talk to maybe something you're used to, maybe a very different topic, but I think hopefully this is quite a cool place to present some of this work to quite a different audience to maybe what I'm used to. So for me, that's quite an exciting opportunity. So Laura gave it a bit of a background to me. What I'll talk about is the project that we've been working on in Svalbard to understand why one specific glacier has been speeding up, but it's quite general because it points to something that's quite applicable across the region that we're looking at. And this is a project that's in collaboration with various institutions in Norway and the UK, as well as Poland. So Aberdeen, St Andrews, Lancaster, and then we have Swansea, Oslo, and TNU, the Polish Academy of Sciences, and NMBU, and we're funded through SAGES here in Scotland, as well as SIOS, who are a consortium of organizations across the world studying Svalbard. And Laura gave a very nice overview about me, and I actually completely forgot that she was going to do that. But anyway, here's my very brief overview about what I'm up to. We have this new initiative here in Aberdeen on interdisciplinary research. So they've hired a bunch of research fellows called Interdisciplinary Fellows to look into grand challenges of the world. And what I'm really looking at right now is to use and develop data and AI techniques to study the world around us. And I'm very interested in glaciers and how glaciers move, but also things like digital twins, remote sensing, big data, Arctic environmental change, machine learning in the cryosphere, all of these kind of topics. I'm just going to put my pointer on. So quite a broad range of interest. What this talk is more about is about glacier dynamics, remote sensing, and a bit of machine learning. So yeah, kind of working and kind of going to be discussing a bit of that. So just a brief contents about what I will be talking about. I'll give you a bit of an intro to the subject. It may be new to some of you, so I'll try and keep it relatively simple, and then I'll talk through the various results that we've been getting and some cool imagery, hopefully, of Svalbard. Processes at the bed of the glacier using some geophysical instrumentation, calving processes, also look back in time, so paleosurges, so past glacier dynamics, and then also a little glimpse into what we're working on in the future, because this is an ongoing project. So just to kind of begin, glaciers are these big masses of ice that dump ice into the ocean all the time, actually. And glaciers are always formed at high elevation. We get lots of snowfall that accumulates over time at the kind of peaks of the mountains. And then as all that ice builds up, the glacier moves downslope under its own weight, and this time lapse is a really nice illustration of this. So we get all that snow and ice forming up here in the high mountains, that then pushes itself and all the ice downslope and then into the ocean. And generally glaciers flow at a speed proportional to how steep the glacier is. So if you have a steep slope, the glacier moves faster. If you have a shallow slope, the glacier moves relatively slowly. There's lots of kind of differences from that general theory, but from a basic perspective, that is how glaciers move. What I'll be talking about today is something a little bit different from that. I'm going to be talking about surging glaciers. Now, that model that we had that I just discussed in that previous slide is what we would call a model for a regular glacier, a normal glacier. So that's what we have here on the right-hand side. So we get ice that builds up, and then as it builds up, the surface slope steepens and all the ice kind of flows downslope, again, proportional to how steep that slope is. What surging glaciers do is something completely different. It kind of it departs a lot from that theory. All that ice, as it builds up at high elevation, rather than speeding up, it builds up in a reservoir zone in the accumulation area. And all that ice builds up and there is no change in the velocity of the ice. But because that ice has to be released at some stage in the future, what happens is rather than slowly discharging ice downslope, it all gets lost in one big sweep called a surge. So all of that ice surges forwards, the glacier advances, and lots of ice is dumped often into the ocean. So these are sudden events. They're cyclical, so they kind of occur over different timescales, and we can generally predict when surges are going to occur if we know this timescale of that cycle. But quite often we don't know what that timescale is, and it very much depends on different environmental conditions. So actually, in practice, predicting it is a fool's game. We can't really do it. So there's lots of interesting questions on glacier physics around this subject that we're trying to understand because we don't really know the full complete picture of what drives these processes. And I'll show some kind of images of what these look like. So what we're looking at here is a time-lapse image from satellite of a radar image of a glacier in Svalbard. I'll talk about Svalbard in a minute. But what happens is usually with climate change, we see glaciers retreating into their fjords. But surging glaciers surge forward, they accelerate, and they're really spectacular. So if we see this run forward again, you can see the glacier is just kind of hovering around. This is the terminus here. It's hovering around a specific place in time. And then because of some trigger, this time there was a calving event, all that ice dumps forward into the ocean. They're really spectacular events, and it's only one glacier at one specific time. Another example, again, we're looking at Svalbard again, this time a land terminating glacier. We've got this glacier here along the trunk, kind of high elevation up here. Some trigger has led this glacier that we're looking at here to surge forward, discharging all of that ice downslope, ending up actually to be a marine terminating glacier, terminating into the ocean. So it went from land to marine terminating. So these events are really spectacular, really amazing events that occur largely unpredictably. And what we're trying to do is trying to understand what causes and drives these surges. And generally, surge-type glaciers are clustered in different regions of the world. If we look at this left-hand panel here, we see all the glaciers in the Arctic highlighted in blue, and all the surge-type glaciers highlighted in purple. This was from a study a few years back by one of the people that we're collaborating with. And you'll notice that there are distinct hotspots of these purple surge-type glaciers. Svalbard here, Iceland, parts of Arctic Canada, Alaska, Yukon area, parts of the Russian Arctic as well, Novaya Zemlya, and a bit of Kamchatka. And generally, we can see these surge-type glaciers occurring in hotspots because they appear in certain climatic regimes, so specific precipitation and temperature conditions that allow glaciers to surge. Now, there are a bunch of other factors at play here locally, such as geometry, ice thickness, bedrock lithology, various different factors that we can't necessarily quantify for every glacier, but generally we do see these hotspots, and it does seem to be related broadly to climate and a little bit of local environmental factors. So we're going to focus a little bit now on Svalbard in particular, mainly because it has a particularly large clustering concentration of surge-type glaciers. And we've been working here. So this is a Svalbard that we can see here in this map in the left-hand panel. And we've been working out in this glacier just over here called Borrbrain. And a few years back, we were trying to hunt down a surge-type glacier because that's what it's kind of like. You need to hunt down these glaciers through remote sensing data. And we found this glacier called Borrbrain that was surging forward and starting to accelerate really quite rapidly. And it was a prime location to start studying a glacier in full motion and during an active surge, because by the time when we started this project, the glacier hadn't accelerated too much, which, because as you accelerate, the ice stretches, it crevasses. Doing field work here is really tough. So we caught the glacier just at the start of the surge and started doing our field work just when the surface of the glacier was still accessible. So we're able to do a field project here as well as using a bunch of remote sensing data to try and characterize the full surge as best we could. So kind of broadly thinking then about what we're doing in this project, I said that the title of this talk was "Why did an Arctic glacier speed up?" But actually it's a little bit more complex than that. The question we should be asking ourselves is, why is it taking Borrbrain, this glacier here that we can see in the left-hand panel, and why is it taking 100 years to start surging again? We know from the past landform record, that this glacier sped up and surged around 100 years ago. So why is it doing it again? Because they're cyclical, we would expect it to happen again, but why now? That's the kind of question we're trying to answer here. And part of the kind of aims of this project is to answer this question, is to study glacier bed conditions using geophysics, to look at how it affects calving, so icebergs falling off the end of a glacier, What impact does an advancing surging glacier have on calving? And also compare to past surge behavior, to compare what conditions were like back 100 years ago to now, to try and see if there are specific conditions that have led to the surge. And yes, we're using remote sensing, but we also did a field project last year in August 2023. That is still ongoing. We're doing more field work again this year, which I'll talk about at the end. Okay, so kind of diving into some of the results then. What we have here on the left-hand side is a map showing the velocity of bora brain over the last few years. So this is the glacier here, this is the velocity map, and we've picked out three specific points on the glacier and generated a time series on the right-hand side. So if we first focus, and we can ignore this temperature precipitation plot at the bottom for now, if we focus on this point just here that my cursor is looking at, this is the time series at that specific point, showing the speed of the glacier from 2015 all the way to 2023, or the end of 2023. Slightly out of date now, just by a few months. You can see that the speed of the glacier up until about 2018 largely maintained a kind of relatively low velocity level of around 0.5, 0.3 meters a day, so around 30 meters a day, which is fairly slow in glaciological terms. But then from around 2020 onwards, we start to see the glacier speed up quite a bit, all the way, if you look at the 2020 values, all the way to 2023, we've seen an almost tripling of the velocity in just 3 years, which is pretty spectacular, really, in terms of how fast glaciers move. The other thing that we see here is we see this really nice, beautiful seasonal change in the glacier velocity every single year. So every year we see a speed up around kind of May, June time. This is all related to meltwater, which I'll talk about a little bit in this talk. And then the glacier reaches a peak midsummer. And then in previous years, that velocity is then reduced in wintertime. It gets colder, so the glacier slows down, which is what we would expect. However, more recently, we've seen a slightly different pattern, that the glacier is now maintain that velocity over winter. Now, that's not really meant to happen. The glaciers are meant to slow down over winter. It's not slowing down over winter now. So this we can now confirm is a surge. It is surging forward, which is very much consistent with the theory that we know of surging glaciers. The other part to kind of recognize here is that if we look at these other 2 points, we can see that the speed up of the glacier further up glacier, so if we look at this bora brain 3 point, the timing isn't the same as near the front of the glacier. Okay, so we can see at the terminus, the surge started around 2020. The speed up has only really started in 2023 further up. So actually what we're seeing is the fact that the glacier sped up at the terminus, and that whole speed up is starting to propagate further up glacier. So the whole glacier now is starting to really accelerate. And we're expecting that pattern to move further up and up the glacier over the years to come. So that's quite an interesting pattern just to kind of start with. There we go. And that's the general pattern that we're seeing. And right now we're seeing the speed up continuing up glacier. So we know that the surge now from this data initiated from the terminus, which is very similar to many other surge type glaciers in Svalbard. And I kind of mentioned that the surge has accelerated over recent years. These are 3 separate velocity maps showing the speed of the glaciers in 2021, 2022, and 2023. If you look at the scale here, the white colors represent around 2 meters a day. So again, we've got the glacier here. We've got the velocity map in 2021 at the terminus. Show the velocity values were around 75 centimeters a day, 0.75 meters a day. And over the last couple of years, that has really sped up. And you can see that propagation really nicely in these maps. So it's just very clear evidence that the whole of the ice mass is now really being taken forward through this surge. Rather than it just being localized, the whole glacier seems to be very much responding to the surge that has initiated at the terminus. So what do we think is happening here? So we need to try and answer this question of, why is the glacier speeding up? Why is it surging? Now, the one question that we cannot answer yet, mainly because we haven't been able to find an answer for it, is what triggered this surge. That's a really big question that we just can't answer right now. I would hypothesize that the surge most likely would have been related to some kind of thinning at the terminus, leading to a smaller buttressing force. I don't know. But what we can start to investigate is what is driving the surge. So we know that as the glacier speeds up, just like you would stretch any material out, it starts to crack. So all of these crevasses on the surface start to appear. As the ice cracks open and you get all these crevasses appearing, when we get to summer, that ice melts and a lot of that meltwater then pools in these crevasses. Now, hydrofracture theory tells us that if you get a certain volume of water appearing in these crevasses, that's going to allow the water to penetrate right through the glacier into the bed. Now, you can imagine if you've got meltwater at the bed of the glacier, that's going to lubricate the surface and it's going to allow the glacier to speed up. And that's exactly what we think is happening here. So we think that as the ice stretches, more crevasses appear, more meltwater appears in the crevasses, more meltwater enters the subglacial hydrological system, and that allows the glacier to speed up. So it's a positive feedback cycle that we think we're seeing here. And this is consistent with other glaciers that we see in Svalbard that are surging. They surge, they open up, more meltwater reaches the bed, and they continue to accelerate. So that water is being trapped at the bed, it's not being released. The moment that water gets released from the bed, we would expect the surge to end. We haven't seen that yet, so we're expecting this glacier to continue to speed up through this process. And you can see the kind of increase in crevassing in these two images here, 2020, 2023, way more crevasses in 2023, the glacier has advanced, it's stretched. And using some drone imagery, and I will talk a bit more about the drone imagery towards the end of the talk, we have lots of really nice examples of melt pooling on the surface. This is a beautiful drone image of part of the glacier where we see this pooling. Now, pooling is suggesting the water isn't getting to the bed yet, but we know from that hydrological theory that we would expect that water to reach the bed at some point. So the fact that we see pooling to us as glaciologists is evidence that that water will eventually reach the bed of the glacier. So the fact that we see so much of it very much points to the fact that we think the glacier is speeding up because of the stretch and because of the melting and the more water reaching the bed. And at this point, I thought it would be nice to start to show some beautiful drone imagery of the glacier we were looking at. So this is what the surface of the glacier looks like in the field. So this is a drone image. We've got all of the ice here. This is the foreland over here. This is the ocean where the glacier terminates into. And you can see that you have lots of crevassing on the surface of the glacier. Meltwater here, all pooling. There's a lot of it, actually, when you start to dig into the details of this. And there's a lot of crevassing, a lot of areas for that meltwater to pool in. So it's a nice illustration, I think, of the fact that we can find much more information of the characteristics of the surface by using these drone shots, and they are just stunning. I mean, I hope this is coming across okay on Teams, but these drone images are just amazing, really, really spectacular. So I've been talking there about how meltwater reaching the bed allows the glacier to slide faster, or it moves faster because of the lubrication of the bed. But I guess the next question is, how would we actually measure that in practice? So we've deployed a bunch of passive seismic sensors on the surface to listen to seismic evidence that might point to or give us evidence of sliding processes below the glacier that's related to meltwater. So we deployed these passive seismic sensors all around the margins of the glacier. We couldn't get into the center where the main stuff is happening because it's just really, really heavily crevassed. But what we do is we move these, we drill these sensors into holes. Sorry, the sound's on mine, so it's quite loud for me. I don't know if the sound's coming across to you. It doesn't really matter too much. We put all these sensors into these boreholes, which melt out by the end of the season, which is okay. And we deploy these all around the glacier. So I'm not a seismologist. I know a bit of seismology, but we have a seismology collaborator who's helping us with this. And what we have here is a kind of normalized area of the glacier where we deployed all these seismometers. And what we were trying to do is to try and localize the or find the location of seismic events across the time series that we were there. So we were there for a few weeks. And we have a procedure where we localize all these events from all these seismic stations, and we get these nice maps like this. Now, the problem with deploying seismic equipment on a glacier is that this is a really tough surface to work on. It's melting a lot. It's deforming. The glacier is always moving. There's lots of wind, katabatic winds coming down the glacier. So we can't, the localization of an event at depth can be quite tough. As you can see here, the black lines show the Gaussian uncertainty with depth on this bottom panel. It's quite hard to locate or pinpoint exactly where a seismic event occurs, but we can do our best. And this is the kind of the procedure that we're looking at, all of these stations and the time series for one specific event that we use to localize exactly where that is. And again, this procedure was developed by our collaborator. If you have questions, then I'll try to answer, but I might not be able to answer exactly. But if we get into the results of the seismic data, then what we see quite neatly are subglacial hotspots of seismicity that we believe could be due to basal sliding. So if we just focus on this left-hand plot to start with, this shows us all of the seismic events with a period of around 1 second or over 20 hertz. So all of the red dots are the locations of the stations. This is the glacier underneath. So it's just showing all of the events that we calculated, but with the colors showing the location of more events in one specific location. And we do appreciate that our seismic network is not that well located. We could have made this into more of a grid, but again, it's really tough doing this on a glacier in the field because you're zigzagging your way around crevasses. So we kind of have to do as best we can with the terrain that we're working on. However, what we are finding in the data so far is that we find these hotspots of all of the seismic events at the surface of the glacier. Now, what we would expect is for there to be a lot more seismicity related to calving. So icebergs falling off the end of a glacier. This is so the terminus is around here. Now, I know that the seismometers are further up glacier. However, the fact that we do see all of these events located in one specific area does imply to us that a lot of the seismicity is related to processes at the bed, which might imply that this is related to basal sliding. Now, if you look at the right-hand plot, these are areas of long-lasting seismicity, so a few to tens of seconds in length. The hotspots of these longer-lasting seismic events are slightly different to the areas on the left-hand side, but they do, again, not appear to be near the terminus, or the terminus being here. So this is where we would expect calving. Instead, they're near they're in the middle of the glacier and at the bed. So again, this points to us that the main seismicity that we're seeing here and hearing here is related to basal sliding, which then correlates with our analysis of the surface processes that we see more meltwater reaching the bed. That is clearly allowing the glacier to flow faster, and this provides us with some not direct evidence, it's probably more indirect evidence, and that tells us that this, in fact, is a process at play here. And if we look back at the theory, and I apologize, these slightly blurry images, but when we look at the theory of glacier sliding or surging glaciers, we have two different types of systems that we would expect. A normal glacier at the end of summer would have a hydrological system below the glacier distributed in channels. So all the meltwater is channelized away from the bed and out at the terminus. Whereas a surging glacier, all of that water is being pulled. It's not being discharged out of the glacier. So where it's being pulled, the glacier can slide over it and allow the glacier to flow faster. And that's what we think is what we're seeing here, that all that meltwater keeps being added to the bed, it's not being released, and it's allowing the glacier to flow faster. And this is the general kind of conceptual model of what we think is going on. Okay, so that's kind of what we think is happening at the bed, but I've talked a little bit about or alluded to calving processes. And we know that for a surging glacier, it's advancing into the ocean, and the terminus of a surging glacier is really steep because we get this big bulge of ice that flows down into the ocean, and that bulge at the very end is very steep. So this changes how calving occurs at the end of a glacier. And this is the perfect time to show yet another fantastic drone video of this. Is a really beautiful subglacial, well, it's maybe not a subglacial channel, but potentially some kind of channelized melting at the glacier bed. And it's really amazing. Our drone pilot was quite confident he'd be fine sending the drone in there. Luckily, it ended up coming back, which was good news for us. And what we have done is we've flown over the terminus of the glacier, taking pictures all the way along, and then we've done some structure for motion work to stitch all of those pictures together and create these orthomosaics and digital elevation models of the terminus, so that we can use this to understand the calving processes driving iceberg calving and fracturing at the terminus. So this is a time series of all of the terminus. You can see there are lots of different crevasse patterns that we can see here. You can see the kind of general longer transverse crevasses all the way along the ice front, but we also get these splaying crevasse patterns, which kind of imply that the glacier is stretching outwards rather than directly in front of us, kind of like a Piedmont lobe glacier. And that's very much more evidence of the fact that the glacier is streaming forward, and where there is no obstruction, it's streaming out towards the margin a little bit as well. So those orthomosaics and those DEMs, we can use them to do some differencing. So this is what we're doing at the moment. This is a little bit preliminary, but I thought I would show it just to give you an indication of the stuff that we're looking at. We have two drone surveys on the left and the right. These were taken on the 11th of August, I believe, around 1 or 2 hours apart from each other. These are the orthomosaics, but what we have as well as that is a bunch of DEMs, so 3D models, that tell us the structure of the calving front. And what we can do is we can difference these models and see where there are changes. So on this map here, we see anywhere there's red, there's been a change in the ice surface. So it says positive, but it's actually negative change. If you get what I mean. So when you lose a bit of the ice front, there's been a positive change in the amount of ice lost. It's kind of backwards. So basically anywhere where there's red, that means retreat or surface elevation drawdown. Anywhere where there's blue, there's been a slight uplift. Although I wouldn't read too much into this stuff out here, because as you can see, sometimes the model, when you stitch all the images together using photogrammetry, if there aren't enough images, the model becomes slightly inaccurate. So I wouldn't focus too much on here. Where I would focus on, though, is the terminus around here. So this is the terminus region, and we can see loads of red areas, which implies to us that there's been lots of calving going on here, which is quite interesting. There's a light red across the surface over here. This implies that there's been a slight surface drawdown of the glacier in this location as well. Now, we don't have a kind of a real feel as to what this means overall. All really to say here is that we're using this data right now to infer what is leading to this calving, these calving events. There might be something related to the drawdown of the surface after the calving event, or even before the calving event that we're looking into. There might be something related to the fact that we see lots of calving events all in the same place. So in this region and in this region, maybe it's something to do with the ice cliff height. We're not entirely sure. But definitely the kind of the structure and the 3D structure of the terminus is really interesting because it's very different to a kind of normal standard glacier. And that's what we're delving into right now. Nothing concrete here, but it's quite nice from an instrumental perspective to show the kind of data that we get. So then kind of moving on to the final aspect of what we're looking at, and that's paleo surges. So paleo meaning past surges. And I said at the start that Bora Brain surged around 100 years ago. And we know that from the submarine landform record, that many years ago, there were some researchers that drove a boat around the field, and they measured a bunch of landforms below the surface, below the waterline, and inferred that the surge occurred around 100 years ago. We don't know the exact timing of that. So the other side of this is that no one's looked at the terrestrial landform record, and this was a good opportunity for us to look at the evidence of past surging. So with a surge, we see lots of crevasses opening up on the surface, but that also potentially leads to crevasses opening up below the glacier, basal crevasses. So where basal crevasses form, that can sometimes lead to an influx of sediment, and when the glacier retreats, it leaves behind these beautiful crevasse squeeze ridges. So where we see crevasse squeeze ridges, that is a signature of past surge activity, or at least past fast glacier movement. At least for this glacier, this would imply this glacier has surged before. So it allows us to look at past ice dynamics, how far the surge has gone, potentially some of the factors leading to the surge in the past, although that's a little bit tricky. But there are some really nice features in the terrestrial landform record that we're using to map out exactly what the spatial pattern of these ridges are. We also have some data on the sedimentology here, which I'm not going to show here, mainly because that's one of our collaborators is working on that, and we don't really have any. I don't think much analysis has been done on that yet. So I'll just show the kind of the mapping that we're doing at the moment instead. This is the drone image on the left-hand side showing some of the ridges. That may be a little bit hard to see, but you can see that you get these really nice kind of linear features that are signatures of the ridges, crevasse squeeze ridges. So what we're trying to do is to map out exactly where all these ridges are. So if we look on this left-hand panel to start with, this is an island just kind of in front of Bora Brain, and we have lots of really nice crevasse squeeze ridges on this island, as well as pooling and a bunch of other features. But they're very nice because it allows us to map exactly where they are, how many there are, and kind of what the spacing is between them. If we look on the right-hand side, we can see a bunch more crevasse squeeze ridges all the way along the foreland. So this is the glacier up here. We see lots of alluvial fans, potentially indicating past kind of stability of the glacier. A little bit hard to see about that. But again, we have lots of crevasse squeeze ridges. Now, I'm not a paleoglaciologist. However, what we have inferred from the data so far and from the geomorphology mapping is that the last surge may have occurred during the Little Ice Age. That's very interesting. So the Little Ice Age was a cold period around 100 to 150 years ago. Because it was colder than it was now, that implies that the surge that occurred back then, 100 years ago, occurred during a very different climatic condition to the surge that is occurring now. That points to the fact that there's different factors at play here that's driving the surge. Now, it appears to be related to meltwater driven forcing, more melt, leading to this positive feedback cycle of surging. In the Little Ice Age, was that the same? We don't know. We would need to have more climatic information on that period of time. But it's a very interesting question that I'm going to leave open for now, because it does point to the fact that different processes were driving surges then and now. So is this the same form of surge? Is it entering a new phase of surge activity? We don't know, but it's a very interesting and open question. The fact that we have this palaeo-glaciological data to inform us on that gives us a nice kind of move into trying to understand the differences between the two, and also the driving processes of surges in general. Okay, so that's a summary of the talk. I'll talk a little bit just in a second about the future stuff, but generally the key findings, or the key preliminary findings, I should say, is that the surge is driven by surface melt reaching the bed and enhancing sliding. I've shown lots of images of meltwater on the surface. We can be fairly certain that meltwater is reaching the bed and leading to or enhancing sliding of the glacier. And we have evidence of that from the seismic data. But it does imply that from the seismic data at least, that calving rates generally are small. So calving rates being the amount of calving at the terminus of the glacier, which is interesting because the other thing that we need to know is how much ice is being dumped into the ocean, because that informs us on the mass balance of the glacier and how much sea levels might rise. And as I kind of mentioned towards the end there, the past surge at Bora Brain appear to have occurred under very different climatic conditions than now. So the open question that we leave is that, was this surge triggered by ongoing climate change? I don't know. That's not a question I'm going to kind of give an answer to, but that is potentially what's happening here. So the original question of this talk is, why did an Arctic glacier speed up? Well, it's surging. It may well be related to the fact that we're seeing more melting of the glacier and more thinning. So we're just going to finish off in this last bit just to talk about what's happening next and what we're doing in terms of monitoring. So this is an ongoing project. This is what I presented here is preliminary work on what we think is happening at this glacier and trying to characterize this surge. But we're continuing to monitor this glacier both in the field and using satellites. So starting off with the satellite measurements, this is again just a kind of snippet of the time series that I showed just way at the beginning of the talk. And you can see this nice seasonal pattern of speed up and initially slow down and then maintaining a consistent velocity over winter. But now we're in 2024, so that's this last bit. Last year we had a really big speed up in velocity over spring. That velocity now of the glacier was undergoing a very similar pattern to before, but slightly surprisingly, the glacier has now accelerated over winter. Now this really wasn't expected. We did not know this was going to happen. We're planning to go out again in a few weeks, and the fact that it has started speeding up again over winter, and we're working with a collaborator who has been working in Svalbard for over 30 years. He told me yesterday that this is the first time he's ever seen a surge-type glacier speed up over winter, which tells me that there's something really cool going on here that we just don't understand. So we really need to get to the bottom of this. So this is interesting. The problem is that as the glacier speeds up, the surface is going to be really heavily fractured again, even more so than last year. So trying to get onto the ice is going to be a real problem this year. But what we're going to do is we are going to go out in April. So literally 3 weeks from now, we'll be out on the glacier again. And you can see from this time series, we always get this massive speed up in May or June time. So we want to get out in April to get all the instruments out and deployed. And we're going to deploy more seismometers on the glacier. But we're also going to install an AP radar. So this is a phase-sensitive radio echo sounder. So a ground-penetrating radar, but it's phase-sensitive rather than just being rather than just focusing on receiving signals. It also measures phase, which is really useful because it allows us to measure sensitive changes at the bed, such as meltwater changes, both through reflections but also through phase changes, which is really useful for us. Because if we can measure how much meltwater there is and what the configuration of the hydrological system is, that really gives us much more information on what we think is happening at the bed that's driving the surge. And it's really going up a gear this year in terms of the fieldwork. We're taking this big helicopter, a Super Puma, out onto the ice, which is going to be rather spectacular. I'm not sure how we're going to land on the glacier with crevasses below us, but we will work it out. And the glacier is going to be fully snow covered with, and the snow is going to be covering crevasses. So it's going to be quite dangerous, and we have polar bears and things to think about. So it's going to be a very complicated field season. But this is going to be a very interesting set of instruments to deploy, and I think it's going to give us some really cool information. And what we're going to do this year, instead of just getting a bunch of data and analyzing the data kind of individually, we're going to do something a little bit different. We have a model of glacier surges from our collaborator, Doug Ben, who made this model. So we have this physics-based model, which is all based on first principles. It's all kind of made encapsulated into a set of differential equations. We're now going to use some machine learning methods, physics-informed artificial intelligence, to combine the data that we get from these geophysical instruments with the models. So what you would usually do with modeling is you would use the data to start a model or to spin it up. We're going to do this in a slightly different way, in that we're going to drive the model through the data. So in a general neural network, so this is a diagram of a neural network, we're going to have a bunch of input layers. That's our data. We're going to bias the training of these data sets using this model. And then what we hope to get at the end of this is some emerging new behavior that tells us something about the physics of the surge. So this is what's happening next. Loads more kind of work to be done on this. We still have this open question of, what's driving the surge, what triggered the surge. We just don't know this yet, but we're hoping that through this work now, we might start to get to the bottom of it. Okay, so I'll stop there. Thank you very much for listening, and thank you once again to EAGE for inviting me to talk. It's been really nice to talk about this stuff, mainly because it's quite new. I hope you enjoyed it. Happy to take any questions.
Thank you so much, William. That was a great presentation. We have several questions on the chat, and we're going to start with Scott M. Scott, would you like to ask your questions? Let's see if Scott can unmute, or I can read his questions. No, okay, so we're going to start with Scott M. question. Are there no surge glacier in Antarctica, or just not enough data to say?
Trying to remember now. It's an interesting question. Yes and no. That's not a very good answer. But so no, in the sense that there aren't, from memory, many, if any. I can't remember exactly. The other side to this is that we tend to think of surging glaciers as these kind of small valley glaciers that surge periodically. However, there are lots of similarities in the characteristics of surges to ice streams. So ice streams are outlet glaciers from the ice sheet that sometimes slow down and speed up. So there's an ice stream in Antarctica called the Cam ice stream, which is currently completely slowed down, and it's barely flowing at all. It's flowing very slowly. That has lots of the same characteristics as a surging glacier during the slow phase, what we call quiescence. So it might actually be the case that the surge theory is very much applicable to larger glaciers, and that surging actually isn't the right way to frame this. There's a new framework to go about this. But at the moment, those two theories are kind of separated at the moment. There are some surge type glaciers in the sub-Antarctic, so on the islands, I believe, although don't quote me on that because I need to try and remember. But they do seem to appear in this like kind of ring around the Arctic rather than anywhere else. A little bit in Patagonia, and also in the Himalayas. So not many, I guess, is the answer.
Great, thank you. Next question is from Michael K. Michael, would you like to unmute, or would you like me to read the questions? Let's see. I guess I'm just going to go through the questions. Is a glacier surge similar to a snow avalanche?
I wouldn't say so, no, because I think a snow avalanche is more generated through some kind of forcing that has led to the snow. Often there's a glide crack in the top of a snowpack that then allows all of the avalanche to flow downhill. It's not really cyclical. The big thing with a surge is that it's cyclical. It happens again and again. We just don't know how long that cycle is, and that cycle changes over time. So it's not quite the same. Actually, an avalanche probably has more in common with an iceberg, because it's all about fracture mechanics and, you know, why does a fracture appear, and why does it, why does that fracture suddenly appear, and why does the snow move down slope? You do get some snow avalanches that are more like glides. They slowly move down, but again, it's not cyclical. I think that's the really key point about a surge. It happens again and again. We just don't know exactly when it's going to happen.
Okay, great. Next question from Laura. Here's Laura.
Yes, yeah, I'm here, so I'm going to ask the question directly. So it's about the seismometer runs. So how do you know how many runs do you have to do, and what are actually the limitations of this technology, and when you are doing the measurements? That's my question.
So when you say runs, do you mean how many seismometers we're actually putting out, deploying?
Yes, and then let's say how many you're deploying, and how many times are you using the same tool just in one place, or you're using this same tool in different areas?
Yeah, so I mean, so the biggest challenge with all of this is the fact, I mean, as you saw in the drone images, the surface is really, really heavily fractured. So what we would usually want to do, and you will probably know this, is that you want to have these nice grid to get a nice grid pattern, so you can actually measure things in that kind of pattern. But we just can't do that. So we would deploy as much as we can, but we're limited by that. But also just, we have to do this all on foot. We need to have all the seismometers in our backpack, and we're walking uphill on ice. So logistically, that makes things really, really difficult, especially on a tidewater glacier where there's way more crevassing. It's a little bit easier on a alpine glacier because the crevassing is there's far little crevassing, so you can actually get nice grid patterns. But in terms of the technology and, you know, what are the benefits and limitation? Benefits, we get to see things that are happening at the bed, which is great because it's inaccessible. Limitations is purely just the fact that these are really remote locations, and also power. Power is a really big problem in the field. Trying to get enough power to maintain the instruments over a long period of time is really difficult. And at the moment, we're relying on essentially car batteries, and taking them out is tough. You know, these are big things to try and lug around with you. So we're trying to find, there are new ways in which you can actually use, you can generate power through hydrogen cells, for example, but this is all pretty new technology that we haven't explored yet, but it could be coming, which would be great because we really need better power options.
Okay. Yeah, no, thanks for answering that. Maybe like a sub question, and when you are actually walking on this glacier, I haven't been in Svalbard, but I have been to Iceland. I did a trip inside the glacier, and I did it with a guide because of the, I guess, dangers that you can actually, when you walk, you can fall through. So is that a challenge as well, that you have someone that guides you where you're supposed to, where it's okay, safe to walk?
I mean, to some extent, it's how would I put this? We're doing this at our own risk, so we are our own guides. So the Bora Brain, this is not a glacier many people go to / anyone recently. So we had no idea where we were going. All we had to go off was satellite images and trying to map out a route from the satellite images and some local knowledge. So very much the case that we have to be working with colleagues that are experienced. I'm not hugely experienced, but I've done enough field work in Svalbard now that I know what to do, and I know that what protections need to be in place. And ensuring that I have other people around me as well that also feel confident is really the best way to go about these things. There are local guides, but they can be useful, but generally we do this on our own back, and we try to keep ourselves safe as much as possible, roping up, because if one of you falls down a crevasse, you need to get them out. So we have to rope up and everything, which is it slows things down quite a lot, but it's necessary.
Yeah. No, I understand. I remember my field trip in Iceland. So thanks a lot. Yes, Hayat, you can carry on with the next questions.
Yeah. Thank you, Laura. So we have a question from Saeed. Saeed, are you with us? Would you like to ask the question directly?
Yes, I'm here. So actually, my question was regarding the crevasses. So do the crevasses increase at the same rate as the velocity of the glacier? Did you find any correlation between the density of the fractures and the velocity of the glacier?
Yeah, it's a really good question, actually. So the crevasses open up at the strain rates of the glacier. So the faster it flows, the more crevasses open up. We haven't mapped out all the crevasses. That actually would take a long time to do. And generally we would have to do that manually. So we don't have the data to be able to correlate that. And to be honest, we don't really need to do that for what we're doing. So we probably won't get around to it. But generally, yes, the strain rate, so the flow at which the glacier is the speed at which the glacier is flowing, does correlate to the opening up of crevasses. There's a few other kind of complications with that. It depends on the texture or the material of the ice. Sometimes you get ice that's near its melting point. Sometimes it's very brittle. So there's a few other factors that play there, and also lateral shear. But yes, generally, I would say that theory does generally hold.
Okay.
And then Said, go ahead and ask your second question.
Yes. So my second question was about geophysical method. If you have thought about imaging the glacier or the bed that is beneath it. So I guess it comes with Laura's questions, and your answer was that it's difficult to deploy a geophysical method there because it's far, because of the conditions that are in this glacier. But I would maybe reformulate this question. I would ask another one and say if it is interesting to image the glacier or the bed that is beneath it, if it brings more information to your analysis.
Yeah, it absolutely brings more information, and it's actually one of the things we're really missing and really want. Believe it or not, someone did drag a GPR along the glacier many years ago, but that data's been lost in time, which is really annoying. So yes, so I guess to answer the question about whether it's important, it's really important because the shape of the bed massively impacts the subglacial hydrology system, which then impacts the surge. So we really need that. The second kind of answer to that is we could, if we could drag a GPR along certain areas of the glacier and do some interpolation. That's okay. The other side to it is that we do have a map of the bed for mass conservation. So there are methods now that use mass conservation approaches to use measurements of mass balance with the velocity to estimate what the bed shape is. That's okay. It's not calibrated against any data, but it gives us something. But yes, if we can fly a plane with a GPR on it, a nice penetrating radar, that would be fantastic. But unless you've got £100,000 or whatever, then I don't think it's going to happen anytime soon. But then the AP res that we're deploying is a GPR, but it's only deployed in one location, so it's not great, but it at least gives us something.
All right. Thank you very much for your answers.
Okay, next question from Scott M. When you say it's moving at 2 meters a day, is it steady or an average over a period of time? For example, it moves 6 meters in one day. That means that it's not going to be moving the next 2 days.
Yeah, I mean that's a good question. It's slightly an average. The time series that I was showing before effectively shows what it does. I say 2 meters a day, but it very much depends on whether I'm talking about summer or winter or spring here. So in summer, it's moving at around 2 to 3 meters a day at its peak. At its kind of lowest level, at least it was moving at around 50 centimeters a day, so 0.5 meters a day. Obviously now in the speed up that we're seeing now, it's just not even going to low levels at all. That speed is continuing to increase. So it's definitely not a static value. I just tend to say 2 to 3 meters a day just to kind of generalize a little bit, but it's not static in time. It's also not static in space. The further you go up glacier, the slower it is. But obviously we're seeing that propagation of the velocity acceleration the further you go up. So it's a number that well spotted. It's a broad generalization, but I tend to just try and use that just to try and sum up exactly what's happening.
Okay, thank you. Another question from Scott, and I think we addressed it a little bit earlier. Could you use ground penetration radar to get a map of the ground underneath the glacier? And we just addressed it. Next question. Assuming that the Earth has been subject to cyclic temperature variation in the past 500 million years or more, wouldn't you expect to find deeper fossil evidence of surge ridges and other evidence related to the accelerated glacier movement in the distant past?
So that is a very tough. First answer to that question is that I can show you this, which is a fossil that we found in the shales around Borbrain, which is really fantastic. So we were just stepping along the landforms, and we cracked open some rocks by accident, and then we saw these beautiful fossils in there. So that was amazing. Cyclical temperatures, 500 million years. At that kind of level, honestly, we don't even know if there are glaciers in this location at that time. Yeah. That's kind of an impossible question, to be honest. I wouldn't have any idea of the state of the Earth at that time. Yeah, sorry, that's not really in my scope, and I genuinely don't even know how to start to answer it, other than to show you the fossils again, because that is cool.
Cool fossils. Great. Another question from Michael K. Surge in winter, growing instability of the glacier, ? Brutal and sudden slippage of a large portion of the glacier, ?
Yes, yeah. So I had a discussion about this the other day, and I guess the acceleration over winter is really peculiar. And as I kind of said in the talk, my collaborator, who, as I said, has been working in this region for over 30 years and knows it way better than me, said that this is the first time he thinks he's seen this kind of pattern, which is really amazing. Like, this is suddenly really surprising, and we have no idea what's going on. We think that there's been a change in the basal slip mechanism. So I'm by no means an expert on this, but generally you have different types of basal slip processes. One's called a Whitman type sliding, another one's called a Coulomb, a regularized Coulomb sliding. And it very much it depends on the shear stress, the driving stress, or the shear stress at the bed compared to the velocity. So yes, what we think is happening is that we're moving into a new regime change in the basal slip pattern, where the shear stress correlates to the velocity, whereas for a normal glacier that wouldn't happen. You would see the velocity slow down, even though the shear stress slow down or maintain a similar level even if the velocity increased. So that then implies that because of that change in the basal slip mechanism, it's allowing the whole glacier to really dump all of the ice forward and discharge faster. So yeah, I guess the answer is we're seeing this change, and we think that's what it could be. We don't know for sure, but we definitely think it's a kind of change like that.
Okay. Peter R. I don't think you discussed whether there was a historic bulge or reservoir increase at the crest of the glacier prior to the surge. Has that been measured?
Yeah, so the bulge that I was mentioning, one of the data sets that we don't have, and I think we will have, just haven't got it yet, is 3D data of the whole of the glacier surface. That's a little bit hard to come by. We do have the drone data, but we don't have that over time. So we only have that for one summer. So what we're trying to get hold of now is a bunch of 3D DEMs that give us that 3D change over time. Well, actually, if you're talking about historic bulge reservoir increase, I don't know if you mean back 100 years ago, but at least now we should be able to generally characterize that kind of surge bulge discharging down glacier. 100 years ago, even with the paleo landform record, it's going to be really tough to get that information out, but at least we can try to infer it a little bit. What I think here is that the whole glacier has been accumulating over time, and then I think the glacier has been thinning because of climate change at the front, and that has led to a loss of buttressing, which we do see in Svalbard glaciers in general, and that has allowed the glacier to slowly speed up, and then because it's a surge type glacier, there's so much more ice that can discharge down glacier, and I think that is what's triggered it. Can't say that for sure, but that's what, from the data, it seems to be.
Okay. Could the little ice age surge be due to the completely different mechanism to the current surge?
Yeah, I think it probably is, and that's the really intriguing aspect to this, is that I think, based on what we have so far, I think these are two different mechanisms at play driving the surge, or it could be the same mechanism, but in a different climate, which points to an inherent internal instability in the glacier itself. So, yeah, it's an open question, but it's a really intriguing question for that exact reason. If it is the internal mechanism, something to do with the shape of the glacier or the state of the lithology, we don't know what the lithology is below the glacier. We don't know if it's bedrock or whether it's the formable sediments. If it's something to do with that, then that implies that there is one underpinning physical mechanism at play. But if it's climate, then I guess you would have to ask the question, why during a cold phase did we see a surge, and now in a warm phase we're seeing a surge? That implies that it's down to local instability, due to internal instabilities. But it is intriguing, I think, that that we see this kind of surge potentially trigger because of ongoing climate change and thinning. So it's kind of a peculiar question that I'm circling, because there seems to be elements of both climate and of internal instability. So I guess the answer to your question is we don't know yet, and I'm really keen to find out.
So Peter shared a paper with us on the chat. He said this paper in first break is due south of your glacier on the other side is Vorden. I don't know if I can say it right. Shows a Permian to Cretaceous stratigraphy. So for anybody who would like to go through the top, here's Peter. Yes. And
I just saw the word dinosaur as well. So I don't know if the stratigraphy on the other side of the Icefjorden is the same, but yeah, your fossil could have been from quite a long geological period.
That's it. Yeah, I know the authors of this paper as well, so it'd be interesting to see them. I'm glad I found a reason to show off this fossil now. I never had a reason before.
There we go.
That's interesting. Thanks.
And it's an open access paper as well. So, you don't need to be an EAGE member, but do join.
Okay, great. So we don't have any more questions. Maybe somebody's writing last questions, but we have a lot of people appreciating the presentation. So thank you so much, William. Let me see who is. I feel like somebody's typing the last question or comment. But while we're waiting on the last comment or questions, you mentioned about your challenges with the electricity and the power in the field. And I was just curious, how long are your field trips? How many days do you stay there on location?
Yeah, it's actually not crazily long, because it's an instrument deployment campaign usually. Last summer we were there for 3 weeks. This year we're only going for a week, because we just need to get the instruments out and then we leave them there, and then we're going to come back later in the year. Sometimes we've done slightly longer if we're doing kind of more measurements and maybe sedimentology work. It very much depends, but at least for this glacier, it's very much been an instrument deployment type of field work, which sounds easy. It's not. The field work we're doing this in a few weeks is logistically it's really complex, because helicopters on glaciers with crevasses underneath snow, it's a lot of planning for what eventually ends up being a very short amount of time. But it's one of those things you don't want to be in a situation where you're going to fall down a crevasse. So everything has to be taken into account. So, yeah.
Yeah, great. Thank you. Let's see.
I think while Cyril he's still typing, but I wanted to say thanks again for a beautiful presentation. I think first of all, I think the visuals were very impressive, because often you come to presentations and if you are not so familiar with glaciology, it's actually nice to see how it looks in reality. So I'm just gonna share a couple news from the local chapter side. And again, thanks a lot for your presentation. It's just to give an update on what's going to happen next in Paris. So we actually have a very busy month in April. We will have 3 events, and one of the events it's the onshore data acquisition, which will be on 16th of April. It will be an online event. So if you're in Aberdeen, London, or elsewhere in the world, you're welcome to join. We'll have 3 speakers from 3 different companies. Then another event that Artem already mentioned, we will have a joint event with that is hosted by EAGE London, and it will be in-person event in Po as well on 18th and 19th of April. There will be 2 sessions. The session on 18th of April will be a hybrid event, so it will be an in-person event in Po, and for the rest of us it will be online. And on 19th of April it will be an online event for everyone, and the speaker of this event will be Dr. Claudio Strobia from Real Seismic. He's highly passionate about the topic, so please do come along. And here in Paris, we will also have an in-person event and in 4th of April, and I call the Minds the Paris. The program itself, it's very intense, and it's about the geomechanical challenges in the industrial carbon dioxide and hydrogen storage in geological formation. So the presentations will be in French and English, which is a little bit unusual, but it's the first time we're doing it, and we'll do it together with SP and CFMR. So it's a really big event. If you are in Paris, then please join. And here is actually a link to it if you're planning to join. And a lot of different companies will be present in this event. So yes, do come along. So that's it from my side. And I see a lot of thank you from everyone. So it seems like everyone is really happy about the event. And again, thanks a lot for coming. And we will consider doing maybe another event in the near future. If maybe Peter wants to host it in Aberdeen, then we can do a hybrid one. if you're keen. I think there's more to it. There's definitely a lot of research done in the area, and it's actually, as I said, it's the first time we talk about this kind of topic. So yes, thank you very much.
Yep, thanks, Will. Excellent, and thanks, Laura and the Paris chapter for organising this.
Yeah, thank you very much. Have a nice evening, everyone.
Thank you so much, Laura, and everyone, and Peter as well.
Thank you. Bye bye.
Cheers.
Bye. Thank you.
Bye.
Thank you. Bye bye.